So, by way of review, we want to talk a little bit about um, infinite series and convergence. And it's important to understand before we get into convergence per se what an infinite series can actually do. And it turns out that it's kind of nice in the sense that infinite series can do the same things that improper integrals can do. And when we get to the integral test for convergence, we'll see exactly why that's the case. But for right now, I just want to make the point that an infinite series can do one of three things. And these are mutually exclusive. It either does one of these things, okay, but it can't do the others. So the first option is that it can converge, by which we mean that that infinite sum of terms is actually equal to a number. So as an example, um, we're going to look at this infinite series from n equal to 0 to infinity of 1 over 2 to the nth. Sometimes people write the indices to the side like this. I'm going to do it because I don't have a lot of vertical room. And we're going to see that this is actually equal to 2. And later on, when we talk about the ratios, the geometric series, we're going to see why that's the case. And we've actually covered that, but we are going to review it. And you notice that this is similar to the improper integral from 0 to infinity of 1 over 2 to the x power dx. And if you review a little bit about your integration formulas, you'd figure out that this is 1 over natural log of 2. So that's the first thing that they can do. Second thing they can do is they can diverge because they become infinite. So they can diverge to infinity. And so instead of looking at the infinite series of 1 over 2 to the nth, if instead I looked at the infinite series of 2 to the nth, you can see that that series gets larger and larger and larger without bounds. And this ends up going to positive infinity. So it does not exist. Okay. And in fact, I'm not even going to write this. We're just going to say that it simply does not exist. And again, if we thought about the improper integral counterpart of 2 to the x dx, using what we knew about improper integrals before the break, we would find out again that this does not exist. The last option is that they simply don't converge. And this is different than diverging to positive infinity. So here, for example, if we looked at the sum of negative 1 to the nth, we'd find that this does not converge. That series keeps on bouncing around as you add successive terms between 0 and 1. And similarly, when we did improper integrals, we found that 0 to infinity of sine of pi x over 2 dx also did not exist. Okay. So here you could say that it does not exist or does not converge. I'll just say does not exist. It doesn't exist for a different reason than this, but it still doesn't exist. And so what does it mean for an infinite series to converge? And so we covered this before the break, but this is important, so I'd like to review this. We have to introduce this notion of a partial sum. And a partial sum is where we're just adding some of the terms in the infinite series. And so we talk about this thing called the nth partial sum. And what that means is I'm going to sum the first n terms in the infinite series. Notice this is a finite series. Okay. So this is what this means. And we represent the nth partial sum by capital S sub n. This is telling us take the sum of the first n terms. And so if we look at this example that we just talked about a second ago, and I look at its partial sums, the first sum in this series, so we're looking at the infinite series going from n equal to 0 to infinity of 1 over 2 to the nth. So this is equal to 1 plus a half plus a fourth plus dot dot dot. And so we can see that the first partial sum, if we just take the first term, we end up getting 1. If we take the second partial sum, which is just adding the first two terms, we're going to get 1 plus a half, or 3 halves. And if we take the third partial sum, adding the first 3 terms, we're adding 1 plus a half plus, and I need to change that to a fourth, and we end up getting 7/4 and so on. If we want to kind of get a concrete representation, we could kind of compute these and get an idea of what they converge to, because what it means now for an infinite series to converge is it means that the limit of the partial sums converges. Okay. So the idea that the infinite sum approaches a finite value means that the limit of the partial sums has to converge. And so if we wanted to kind of get an idea of what this actually looks like for this specific example, okay, this is just some basic MATLAB code, and I'm taking the partial sums, okay, so this is going to be the first term in the series that I'm adding, and this is going to be the last term for n that I'm adding. So here I want to look at partial sums from k equals 0 to n, where n goes between 1 and 11. Okay, that's the idea. And this is going to actually have to be this. Yeah. So I start off with a lower index and upper index. I initialize my partial sum vector, and then all I do is I just set up a for loop. And the idea is that at each iteration in the loop, I'm increasing the index here. I'm computing the next term in the series, and I'm adding it to the old partial sum to get the next partial sum. And if I go ahead and I plot these partial sums, these are the first couple partial sums. So the first partial sum is when n is equal to 0, and sure enough we can see that we get 1 here. Second partial sum is when n is equal to 1, and sure enough I can see the first two terms is 3 over 2, or 1.5. Third partial sum, I'm adding n equal to 0, n equal 1, n equal to 2 terms, and I can see that I get 7/4, which ends up being 1.75. And so if we ask the question now, does the limit of these partial sums, so as n goes to infinity, does it seem like these partial sum values are converging to a particular number? And it does, right? It looks like, in fact, they're converging to 2. That's what it appears, all right? But the problem is that this isn't a proof. And in fact, there are a lot of infinite series of partial sums converge very, very slowly, and it's very deceptive. So we want to try to, justify that answer a little bit better. Okay. So Here's going to be our outline for what we're going to do. Um, the two big questions that we have to answer. The first one is, does an infinite series converge? And it turns out that we're going to introduce a bunch of tests that will tell us when an infinite series converges. And one of the most important things that we're going to have to know, and you can in fact use this handout and fill this in, is when can we use the test? And what we're going to see is that tests for convergence of infinite series are a lot like deciding which method to use for integration. So let me just expand on this for a second. So, for example, when you did integration, you had some integral here, and you had to figure out how to do it. And so we had all of these different methods at our disposal, right? So we had, integration by parts, U sub, trig sub, trig integrals, method of partial fractions, right? And so on. And how did you determine which method to use? Well, you looked at the form of the integrand, right? So, if, for example, you had an integrand that looked like this, maybe you had x over 1 minus x squared root of, you'd say, okay, I have a composition of functions, and I have the derivative of the inner function basically in the numerator up to a constant, so I'm going to try u sub. We're going to use exactly the same sort of approach here. We're going to have, excuse me, infinite series here. And here we're going to be interested in, does it converge? And so we're going to have a bunch of tests. And these things that are listed here are all the different tests. There's actually many, many more, but we're just going to limit ourselves, okay? And the question is, what sort of test are you going to use? So we have, we're going to have, a root test. We're going to have a test for non-convergence. We're going to have an integral test, root test, a ratio test, and so on. And the question is, which test do we use? And exactly the same sort of logic applies. It's going to depend upon the form of the summand. So if, for example, we have r to the nth, we're going to see that we could use the root test. Now, one thing to bear in mind is when you did integration, sometimes you could use more than one method, right? So in this case, we could use u sub, but no doubt some people, the thought occurred to them to do trig sub, okay, because I have a 1 minus x squared, so that kind of suggests that we do a sign substitution here, right? We're going to see the same thing is true for an infinite series. We're going to see that although the root test might be your first go-to, that in this case we could also use the ratio test. And of course this won't make sense right now, but the point I want to make is that very often there's more than one test, just in the same way that there's more than one method to use for integration. But in both cases, this question of when can we use it is going to really center on what the form of the summand is, okay? And so the last question we want to ask, of course, is if an infinite series converges, what is its value? And we're going to see that we're actually somewhat limited in the type of series we can answer this question for. The one that we're going to answer it for most certainly is one called a geometric series. We're going to actually give a formula for that. And we're going to introduce some specialized series that we're going to be able to evaluate, such as the telescoping series. And there are other series that maybe if we have time we'll get into. One that's kind of famous, but it's not really that big a deal, is the alternating harmonic series. And if we have time and everything, we may talk a little bit about that, but we'll see. Okay, so that guys kind of gives you an overview of what it is that we're trying to do when we talk about convergence, and specifically the approach that we're going to use. This is a good table to keep and fill out and really get to understand.